Our first speaker is going to be Tom Marcusick, who many of you have seen at the Austin Forum before, both in person and online. He's the founder of Firefly Aerospace. He can't be with us tonight because he's busy trying to launch rockets. So schedules change. He planned to be here. We're going to bring him up on Zoom instead. And then we're going to turn it over to Dr. Maura Bajah. He's a professor at the University of Texas at Austin in aerospace, but you may have also read about him in the news a lot as the co-founder and chief scientist of Privateer. He'll come and talk about what Privateer does. If you haven't heard about it, it's really cool. Then we're going to take a view farther out into space and bring up Dr. Michaela Bagley. Michaela is a postdoctoral researcher in the astronomy department at the University of Texas, and she's going to share with you some of the marvels of the James Webb Space Telescope. So with that, let's bring up Tom Marcusick on Zoom. Everybody.
Okay, can you hear me? All right, I'm not actually getting any audio feedback from you. So, okay, hold on. All right, I guess y'all can hear me, so I can't hear you. So, but I'll get into it. First of all, again, my apologies for not being there in person. Truly, to connect in this forum, I love being there, talking to people directly, and I hope I'll have an opportunity to do that again in the future. As you introduced, I am at Vandenberg Space Force Base right now. We've been trying to launch our Alpha rocket for the last 2 days. It's a really big event for the company. It's our second launch, and it will be hopefully our first full success of getting to orbit. So it's a really big deal for the company. And I'm going to hang out here for the rest of the week as we prepare for our next opportunity, which is actually going to be at 2 a.m. Austin time next Sunday night. So we have a window from midnight to 2 a.m. here, so 2 to 4 a.m. So for any diehard Firefly fans, burn the midnight oil on Sunday night and watch that first launch attempt. It should be pretty cool. It's interesting that the name of our mission, I named our mission To the Black. That's a little bit of a tip of the hat to the Firefly series, where they call the space the black. And it turns out that our rocket refuses to launch unless it's completely black outside. So we're going to be doing that launch right at midnight. So it should be really interesting and cool, a good show. So hope you'll tune in to that. If I were there, I planned on doing a pretty wide spectrum of topics associated with space and being an entrepreneur and kind of the greater mission and what it means for humanity. Hopefully I'll get to do that in the future. What I wanted to do with this brief intro today was just get to kind of the main point about what we're doing at Firefly and what this thing called New Space is, talk about how we got here briefly, and then just really hit some of the high points about what the implications are of New Space and why it's a big deal and why it's not just about man on the moon and how it can have a real positive transformative impact on society. So just starting from the top, New Space is this movement that Firefly is part of. It's a revolutionary movement. And like all revolutionary movements, it aims to subvert the dominant paradigm. And in this case, the dominant paradigm that we're trying to subvert is space exploration and space economic development. And what that means is we're really trying to dramatically lower the cost and increase the frequency of access to space. It's really interesting. When I started this, I was an early SpaceX employee, and subverting the paradigm meant basically providing a much better alternative to what big governments and big aerospace companies were providing. It's kind of funny now that I was actually approached in the parking lot as I was getting ready to go launch the rocket yesterday by an individual, and he came up to me and was imploring me and Firefly to subvert the dominant paradigm, which is to beat SpaceX now. So it's kind of come to the second generation point where we're not, it's not about, changing the way big government and big aerospace companies did it, but it's actually changing how the first generation of New Space was doing it. Some other attributes of new space are that it's very much a 21st century and American activity. It was really only at the beginning of this century that Elon stood up and really took it seriously and really got together a group of very talented people and put a huge amount of money into it and really birthed what we call new space. It happened here and it continues to really only flourish in the United States for whatever reason. That's maybe something we can talk about more later, or maybe I can talk about more in my next presentation. But it is private and entrepreneurial. And again, maybe that's why it's such a big deal in the United States. We have a very strong entrepreneurial base here in the United States. And there's a lot of capital that's can be brought from parallel industries to bear on this industry. So how did we get here? Again, I mentioned Elon at the beginning, and we do have to give Elon credit for this. I mean, he was the first one to really lay it all on the line and get it all to work correctly. And I was really fortunate to be part of that team. I was there when we launched the first Falcon 1 rocket, and we crashed rockets. And Elon just stuck it through, really almost to the point of personal bankruptcy, and ultimately we're successful, and it really changed the world. But I should also mention others like Blue Origin, Virgin Galactic, Stratolaunch. Those were some of those other first generation companies that really had a big impact. So what we have now is very exciting. We have a whole group of second generation companies. These are people like myself that came out of these first generation companies, and I pretty much worked for all of them. Can't hold a job. But the people that are coming out of those first generation companies have ideas about how to do things even better. And there's probably a good 10 at least viable companies coming out of these first generation companies, and there's probably 100 others that are out there and trying to get going as well. I think another interesting thing about new space that you should keep in mind is it's not just about fire-breathing rockets. It's actually spread beyond the launch vehicles, but actually to the satellite technology. That's where really you're going to see the most impact in your day-to-day life. It's not in the rockets that we're shooting off into space, but it's the satellites that we put up, it's the landing systems, it's the human exploration systems, and all of those things have now been privatized and are really in the hands of new space as well. And the most exciting work is going on there. So ultimately, this economic activity, and I will just wrap this up by saying that economic activity, I think, is really, really, really important. It's not just man on the moon. The exploration part is exciting, but what we do is we create thousands and tens of thousands of high-paying 21st century jobs, and I think that can have a very strong positive impact on society. I think having a great job gives a lot of dignity. It strengthens families, and I don't think we should understate the value and importance that these new tech companies in the space are having. But just to, again, wrap it up with the big picture thing, I would ask everybody to think about what a world or what an existence would look like if we had unlimited resources. I know we're going to have some speakers talking about what's out there, but at the end of the day, if we can figure out how to move around the universe, humanity essentially has unlimited resources. There's really not a lot to fight for, and like to think about how that would unify us as a species. So I'll just wrap it up there. I look forward to answering any questions as we get deeper into this, and I look forward to hearing from the speakers that are going to follow me.
Jha from the University. Yeah, okay. All right, so
Thank you, everybody, for being here, and it's an honor and a pleasure to be with you. So my name is Morba Jah. I am a professor at the University of Texas at Austin in aerospace engineering and engineering mechanics, and I am a co-founder and chief scientist of this company called Privateer. I'm an astrodynamicist, which I will explain here shortly, and I'm a space environmentalist. Astrodynamics is really the science that studies motion of stuff in space. You know, what motivates the stuff to move, why does it move the way it does, and that sort of stuff. So that's my gig. And space environmentalism is something that I kind of coined up a few years ago, and I'm going to talk about that next. So in 1957, we launched the first satellite, Sputnik, and that pretty much changed humanity forever. Now, in 2022, we're tracking about 30,000 objects ranging in size from a cell phone all the way up to the space station. Every single one of those dots that you see on that website, it's called Wayfinder, every dot is a human-made object currently orbiting the Earth in some orbit. If, John, I don't know if with your mouse, if you can kind of like zoom in or zoom out and that sort of stuff so that people can get an idea. How about you zoom out? I think zooming out will be good right now. There we go. Excellent. All right, keep on going because people need to see the amount of junk up there. So, thank you. You can stay right there. So, out of the 30,000 objects that are being tracked, 5,000 work and everything else is trash. Okay. That's not even the worst of it. So the thing is, we hypothesize that if we go down in size to a speck of paint, okay, if we count the number of objects going down to a speck of paint, we believe there's about 1 million, okay? Speck of paint might seem of no consequence, but bullets are small and they do a lot of damage. Specks of paint are traveling at 15 times the speed of a bullet. And if that hits an astronaut or even a satellite that's providing a service or a capability, it's a bad day. So who cares about these satellites? Well, let me tell you. So we have these robots in space called satellites, and everything from position, navigation, timing. We have a war in Ukraine. Satellites are providing unique data about what's going on the ground. Humanity knows more about itself because of these robots in space than from any other source of information. And more of our technology and infrastructure is being launched into space. You heard about Elon and SpaceX. He has these satellites called Starlinks. Actually, out of the 5,000 or so satellites that are working, over half of those belong to Elon. We have doubled the number of working satellites just in the past 3 years. And more people are launching stuff as quickly as possible because there's a lot of money to be made in space. It's kind of like the new bonanza, the new gold rush. And even though there are no deeds or titles to orbital space, it's kind of like first come, first served, because physics tells us that two things can't occupy the same space at the same time or bad things happen. So these 30,000 objects, they can at any given time collide with a satellite providing these services, and then the service is gone, and we just don't have these things sitting on shelves just ready to launch. The other thing is that most of those objects that you see there are never going to come back. It's kind of like pollution in the ocean, kind of like plastics. Something dies on orbit. It doesn't just slow down. It keeps on going at very fast speeds. So imagine being on a highway, you're driving, you're going at, let's assume you're going the speed limit, okay? Let's assume. You run out of gas, the car keeps on going at that speed, and basically you just get another car that has a full tank and you happen to hop on that and you just keep on going. Imagine driving down the freeway with a bunch of cars with no drivers going at high speed, and every once in a while these things bump into each other and create debris, and all that debris is now traveling at that high speed, and that debris collides with other debris and creates more pieces, and all that stuff is traveling at these high speeds. So the carrying capacity of any given orbital highway is becoming saturated. That means that at some point, if we continue to behave this way and Just launch stuff without coordinating and planning with other people, because there are no space traffic rules. Here on the ground, you know when to turn left, right, what the stop sign means, that sort of thing. In the air, we have rules. On the ocean, we have rules. In space, there are none. You just get to launch and just do kind of whatever you want. And, you know, the strategy of hope that it's all going to work out. That's not a great strategy. We're launching more and more people into orbit. And, you know, people are saying, oh, you know, space tourism, that's really cool. I want to get on one of these rockets and that sort of stuff. Well, I'm going to tell you that I don't want to be one of those people. I have friends that have gone up, Dylan Taylor and other people, and I applaud them for their courage. But unlike getting on a plane and just going from here to, say, you know, Rome, you hear the safety briefing and say, in the case that the pressure in the cabin decreases, you're going to see these things pop from the ceiling, these masks. Case of a water landing, here's your flotation device kind of stuff. In space, there's going to be an extra thing on the safety briefing. Oh, by the way, there are all these objects that we're tracking, most of which we can't, which are kind of like random bullets, which might pierce your spacecraft, and you're probably not going to make it, maybe, but good luck, have a safe trip to space. That's what every single person being launched has to face these days. That's not so good. So what I'm saying is that these orbital highways where we have satellites that are providing these critical services and capabilities that each of us depend upon are in jeopardy of becoming saturated. We can't use the orbit. It threatens lives of people being launched, that sort of stuff. So where's the good news? Oh boy, that's tough. Let's see. There's another website, the conjunction one. Maybe if you could refresh that, let's see what happens. So how busy, it's going to happen. Yeah, just like, okay, cool. So how busy are these orbital highways? So what you're seeing is a live prediction over the next 20 minutes. What we're asking ourselves is the following question. Out of, say, 20,000 objects, which pair of any of these 20,000 is predicted to come within 6 miles of each other in the next 20 minutes? And if so, show me. That's what you're saying. These are all predicted crisscrossings within 6 miles of each other just over the next 20 minutes. Green dots are when both pairs are working. Yellow dots, one is working, the other one is dead. And red dots are both objects are dead, so we hope that they don't collide with each other. Okay. We are hoping that these things don't collide with each other. There's a histogram. There are 3 histograms. The one on the upper far right is relative speed. For those that can't see the numbers, the spike is at 15 kilometers per second. That's 15 times the speed of a bullet. Most of these things are crossing each other at 15 times the speed of a bullet. If they hit, bad things are going to happen. So what we're doing to the land in terms of landfills and that sort of stuff, we've done to the oceans in terms of pollution, and now we're doing to space. Every 3 weeks, Elon's launching 100 satellites into orbit. Every 3 weeks. Nobody's telling you, nobody's asking you, but hey, you might have satellite internet. It's not that it's bad to launch all these things. It's that it's being done in a way that is not coordinated, and there are no traffic rules. Most of the satellites are not reusable, they're not recyclable, and so they're just contributing to a growing number of junk. So with my work, what I'm trying to do is I'm trying to motivate the development of a circular economy in space, meaning, can we come up with mechanisms to prevent pollution? Can we minimize single-use satellites, just like minimizing single-use plastics? Can we design satellites that can be reused and recycled so that we can minimize the detriment to the space environment as an ecosystem in and of itself, and make sure that we can all have use of it for the long term? And whenever humanity gets off this planet to go explore other places, which needs to happen, that there's a way for that to happen. I mean, I don't want to be too morbid, but if we don't figure out interstellar travel, humanity has a definite end, because eventually the sun fizzles out. Sorry, it'll be in a while, but it'll happen with absolute certainty. So we have to become interstellar. That has to happen, or else humanity ends. If we continue to behave this way, we're not going to make it. Thank you very much.
Thank you. And more will be back up on stage in just a bit to answer questions, some that I'll ask and some that we'll select from the audience. By the way, I hope everybody sleeps well tonight after what Moraba closed with, because my daughter didn't. I made the mistake of telling her when she was 5 years old that the sun would go nova, it would shed out, it become a red giant, it would envelop the inner planets in its orbit and life would cease to exist. She didn't sleep that night and her mother said, thanks a lot. Thanks for teaching her astronomy. I said, it was 5 billion years. And she said, you know how she is. She gets it from you. So with that, I'm very pleased to introduce Dr. Michaela Bagley, a postdoctoral researcher from the University of Texas. They are an expert on imaging of certain experiments being done with the James Webb Space Telescope. So I want to bring, right here. Come on up, Michaela. Please welcome Michaela.
Thanks, everybody. It's awesome to be here. I've never been to the Austin Forum. I didn't know about it, so I'm really excited to learn about this. So I'm going to talk to you, I think, today about two sort of very different, well, they're related, but very different things. I'm a postdoc at UT Austin, and my specialty is in early galaxy evolution. So I specifically study, what I would like to find are the very first galaxies to form in the universe and try to first of all, find them, which is a whole problem in and of itself, and then try to understand how they formed, how quickly are they able to form stars, build up their gas, build up their mass, and turn into things that are like the Milky Way today. And so up until about, I don't know, a month and a half ago, the best tool that we had to do this type of science with was the Hubble Space Telescope. It's being in space makes the telescope a much more sensitive instrument for a number of reasons. It also lets us look into the infrared light, and I can talk about all this more. It lets us look at the universe through infrared light, which is just like looking at it through heat. Which can give us a lot more information about the early universe than looking at things through visible or ultraviolet. And so up until for a very long time, we only had Hubble, and Hubble is amazing and I love it and it's wonderful and it's far exceeded all of our expectations for it, but it has limitations when it comes to studying the early universe. And with Hubble, the best that we could really do was hope to find galaxies. We couldn't really study what they were made of. It was very difficult to figure out how old they were or how far away they were. Once you sort of push Hubble to the limits of its sensitivity and what its instruments are capable of, the best that we were really able to do was find sort of candidates galaxies in the early universe. And by candidates, I mean, we would find them in imaging and we would say, man, I really think this thing is really far away, but it's possible that it's actually a lot closer. It's possible. I think it's very massive, but it's probably but it's possible that it's actually just a lot smaller than we think. So we were very limited in what we were able to detect. We were limited in what we were able to detect and limited in what we were able to learn about those galaxies. So then we launched the James Webb Space Telescope and everything changed. And I will never be able to express how exciting this telescope has changed, how much it has changed astronomy and how exciting it is as an observatory. And so what I'll sort of switch to talking about now is JWST, less on the science, although I'm happy to answer questions about anything that I study, and a little bit more about the telescope, the observatory, and the instruments on it. So the telescope is it's been in the works for about 30 years. I've been directly focused on preparing for it for about 12 years. And it finally launched on Christmas Day. I don't know how many people woke up at like 6 a.m. to watch it. I certainly did. And it was like, honestly, the best Christmas gift ever. It was a flawless launch. It actually could not have gone better. we like to say that the telescope, its launch and its deployment was actually better than perfect. And by that, I mean, we had expectations for how it would go. We had models for what we sort of a benchmark. This is how good we hope it gets. And it did even better than what we thought was possible. So the launch was amazing. The telescope was perfect. They got the launch vectors so good that the telescope didn't have to use much fuel to do course corrections to get it on its final destination. And that means that the longevity of the telescope, it was originally planned to be, or it was sort of a requirement that it lasts for 5 years, but we can now look forward to more than 20 years with this amazing telescope because of how well the rocket launch went, in large part. And then, you know, the excitement was, we were excited, but the journey was not over. We had about a month, about 29 days of like pure nail biting terror, because this is I think, at least for space exploration, the single most advanced engineering feat that we've ever launched. It has thousands of moving pieces, whereas Hubble only has a handful and Spitzer Space Telescope only ever had like 3 moving pieces and only 2 of them ever worked. So this was a huge, which, you know, was a problem. So this was a huge sort of leap in the engineering feats of what we launch into space. It had 344 single point failures in its deployment process of how it would get, it was basically a space transformer. It's such a big observatory that you can't fit it in a rocket. The fully deployed telescope, including its sun shield, is the size of a tennis court. The mirror is 6.5 meters in diameter, which is taller than the tallest giraffe. And it's just incredible. So through that month of sort of nail biting terror, it slowly unfolded. And we're going to see a video in just a second about, but it's too fast for me to explain what's happening. So I'm going to try to say briefly what happens first. So it gets launched and it separates from the rocket. And one of the things that we didn't know as the astronomers watching the launch was that they had kept a camera on the rocket so that you could see the telescope separate. And I started crying. And then the first thing that happened was it released its solar panels. So it was running on battery power up to this point. And the first issue was, if that solar panel doesn't unfold and it's all automated, then that telescope never gets any power and it's dead on arrival. But not only did it unfolded on schedule, and we got to watch it unfold from the rocket. So that was live. So that was incredible. Then it started for the next month. It slowly unfolded its sun shield. It slowly unfolded its mirror. It slowly unfolded all of these little gadgets and pieces that are required to make all of the systems work. And that's where those 344 single point failures were. There were about 50 major deployments that had to happen. And those involved something like 200 separate motors and little movements that controlled all of this. They actually, and during this process, the whole telescope is cooling down to very, very close to absolute zero. At its coolest point, I think it's about 39 degrees Kelvin, which is very close. The reason we need it to be that cold is it's an infrared telescope. We're trying to look at the universe in heat. And so the telescope itself and its instruments have to be very cold, or else we're going to be seeing the telescope and not the universe. And so that's why we have this huge sun shield. And so I think now maybe we can watch the video of it unfolding. This is the whole deployment process. I'm going to talk while this is going, if that's okay. So, yep. So that's the solar panel that comes down. Then the next thing, that's the communications array. That was the second thing, dead on arrival if you can't communicate to the telescope. This is the boom that's going to hold the sun shield. They have to raise the telescope away from the sun shield to create space so that it can actually cool down. The thing that just unfolded is like a rudder on a ship that keeps, it's the momentum flap that keeps the telescope from moving too much. And then as these booms move out on the side, it very slowly pulls out the sun shield. It's 5 layers of incredibly thin material. The material is about I think it's like 1/1000th of an inch thick, and there's 5 layers. And the way that they create this shield of all to protect the telescope from the sun is by slowly tensioning, very slowly. I mean, this took days, very slowly tensioning all of the layers. Then they bring the secondary mirror down on its boom. Then they open up a little back flap on the end so the instruments can cool off. And then they bring out the primary mirror. And I think so I think that's the end of the video. So that was just the telescope. Then after this, they had about 4 months of commissioning the instrument. It took them a full month to get the mirror, all those 18 segments, those 18 hexagons. They all had to come out. Oh, that's cool. They all had to come out of their little like holders. Then they had to first of all, they had to figure out where they were all pointing. I mean, they took pictures of the sky to figure out where each segment was even pointing. Then they had to phase them all together to teach the telescope how to act like one mirror and not 18 separate mirrors. And then they very slowly went through and commissioned all of the instruments. And I could talk about that for hours and I won't, but it's incredibly, I mean, it really was a very fascinating sort of feat of engineering. So I said that JWST was way cooler than HST, and HST or Hubble is sort of my baby. So I'm saying this very, it's a betrayal. But so what these images are going to show is the difference between what you would see with Hubble and what you see with JWST. JWST provides us a much higher resolution. It also provides us an entirely different set of wavelengths of light. And so we're getting way more information about what we can see. And so this is the image from JWST. And as you slide back, this is what Hubble would see. And a lot of this has to do that we're looking in redder wavelengths of light. So we're getting more information about dust and star formation and some of the gas in the galaxies. And a lot of it is also that the images, the detectors are just much, much, much higher resolution. They have a ton more pixels per each section of the sky. I like this one. It's like night and day between Hubble and JWST. Okay, cool, thanks. And then could we pull up one of the images from, I forget what it's called on the slide. The Sears mosaic, sort of the big wide fields. Okay, cool, thanks, this is perfect. So what I've spent the last month on is actually taking the data from the telescope, processing it, cleaning it, and turning it into this mosaic that you see in front of you. So I'm a member of a team called SEERS. It stands for the Cosmic Evolution Early Release Science Program. And the idea was to sort of demonstrate the capabilities of multiple instruments on the telescope all at once. The idea was to, so we can learn, and also to teach the whole community how to use the telescope, how sensitive is it, and how do all the instruments work together. And so I think this is still true, but for a very short period of time, this is going to be the widest image of the universe so far taken with HST. It's in the EGS field, which is near the Big Dipper. And if you hold your thumb out at arm's length, the area of the sky that's covered by this mosaic is the size of your thumbnail, just the top, just the little tip, not the full thumbnail, just the little top. And so we've got some links there so that you can explore some of these images in more detail. But what's really cool with this is to click on the high resolution images and just keep zooming in, because basically everything that you can see in that image is a galaxy. There are a few stars, and as an extragalactic astronomer, I don't like stars. But everything else is basically a galaxy. There's galaxies, there's thousands and thousands of galaxies in this image, way more than we expected. We've highlighted a few examples that you can see sort of zoomed in different regions of what you can see in this image, but I highly recommend people check out these links and download the images and just keep exploring. You'll lose hours, I promise. Yeah, and so I think do I have like 2 more minutes? Okay, cool. I think there was one more image maybe that showed yes. So this is the same mosaic, but now we're going to zoom into one of our early discoveries with the telescope. Our team found, oh wait, this is a different one. Yes, that one, thank you. It went away. Our team found, we were looking for these early galaxies in the universe. It was the first thing we wanted to look for when we got the data, and we actually found one. It's incredibly exciting. So this is showing a zoom in of different areas, and when you get to the lower right, you're looking at, it's very unspectacular. If you work on galaxies that are closer, they're much more beautiful. They've got these spiral arms, they've got all these colors, but that's not what I do. I work on these tiny blobs, and this tiny blob is an image of a galaxy that formed about 250 to 300 million years after the Big Bang. So that sounds like a lot, but that's almost no time whatsoever in the period of the universe. So this is a galaxy that got very big, very fast, very shortly after the universe formed. And right now, with the models the physical models that we have of how you form galaxies, we can't explain how you make something this big that quickly, but it's definitely there. And so this is our very exciting results. It looks a lot less impressive than all of the other galaxies, but it's a really cool scientific result. So thank you.
We actually finished just a little bit early, so we've got some time for questions that from the audience. I had some questions for them, but there are so many great questions that people have submitted. I'm not going to ask mine. I'm just going to ask your questions of them. So if Maura would come back and join us on the stage. Nope, we still need. Oh, all right. So Michaela's getting water, Morba's coming up, and I have questions for both of you. Some of these are also for Tom, but because of AV limitations of hybrid presentation Q&A, we won't be able to get his answers to those tonight, but we will see what we can do about getting those for the Austin Forum Slack workspace. So again, thank you both for being here tonight. Lots of great questions ranging from industry to alien life to unity on Earth to you name it. Let's see. Actually, I'll go ahead and ask one of the fun ones right at the beginning. Someone phrased it in terms of the Fermi Paradox. With the recent discoveries from Hubble and Webb Space Telescope showing more and more planets in continuously habitable zones, when is it that you think we may actually find some evidence of some form of life?
Yeah, not my field of expertise. I think we will find evidence this year, indirect evidence of the possibility of life sometime in the next year or year and a half. And what do I mean by that? I think we will find evidence of elements or compounds that we think can only be created by life, but we don't know for sure that they can't be created through some other mechanism. And so it will be indirect in the sense that we won't have confirmation of alien life, but I agree, it's a numbers game. If you have that many planets and you have that many that you can have liquid water on, it is only a matter of time, but they're all very far away, and that's really, really hard to observe.
Morba, do you want to weigh in on this one?
Yeah, I mean, no, I don't want to just, well, I guess I will be making up something because just, people just don't know. But I think when people are looking at these telescopes and the data, they're not realizing that that's not a current picture of the universe. Like that's something from a really long time ago. So if we see life or whatever, it's like, it's going to take photons a really long time to get to us for us to see some of those things. So. Sorry.
Marva brings up a great point. We've only been emitting television and radio signals into space for what, about 100 years, ballpark, which means that if someone else started at the same time and they were more than 100 light years away, we wouldn't see it anyway. So question probably more for Moraba on this one. Firefly was named after their aspiration to launch lots and lots of small satellites. Is this kind of mission at odds with reducing space junk and creating a circular economy in space?
Yeah, so I don't think that the number of satellites in and of itself is the problem. It's the way in which we're doing this sort of stuff. It's the way in which we are launching things kind of uncoordinated. And I would even say, one of the things that really inspires me is environmentalism and sustainability from indigenous perspectives, traditional ecological knowledge. And one of the things that certain indigenous people do is they basically say we have to have a successful conversation with the environment because we're in existential crisis all the time. Like if we don't do that, we don't live. And when they interact with the environment, they do so in a way to allow Mother Nature to give them feedback on their actions so that they're not behaving in a way that's detrimental to sustainability. We in Western civilization and people launching satellites tend to believe space is big, who cares, everything's going to be okay. And that is basically a slap in the face to real sustainability and environmentalism because of what I just pointed out.
I agree.
Okay.
No, I mean, I think like there are like NASA has procedures whenever you launch a telescope, whenever you launch a satellite, you have to save enough fuel at the end of its life to be able to do a controlled reentry. That's not quite the case for JWST because it's so far away. I didn't mention it, but it's 5 times further away than the moon. So we won't be bringing that back. But anything that's in low Earth orbit, you have to plan for how what you're going to do with it at the end of life. And so I sort of see launching satellites is awesome, but what do you do? Bringing them down, coordinating with how they're acting when they're up there.
So I think I love what you brought up because people don't realize that the reason for the whole controlled reentry, right, is we hope that these things burn up in the atmosphere. But the thing is, they don't always do that. And when you try to intentionally, make it come in steep to burn up and the stuff survives, bad things can happen. I mean, there's a Chinese rocket, the Long March 5B, that basically this is a school bus sized object. It wasn't controlled to reentry. It was just left to Mother Nature to clean up. This thing could have fallen. I think they predicted somewhere in like Northern California, people were trying to figure out, is this going to land over a populated area? School bus sized object traveling at kilometers per second, landing in a city, bad news. But most of the time, because, Earth is covered mostly by water, basically we're polluting the ocean. We're like, oh, well, it's not falling over people, so it's okay. So we aren't really behaving in a sustainable manner.
Great, thank you. Enrique Lin Chao has a great question. Given that most of the innovation is happening in the US, will this lead to a monopoly and access for citizens of this country only, along with colonizing space real estate? How do we ensure that space remains accessible for all and not only people here? And so I wish Tom was here to help answer this question, but I think Moraba may have some opinions on it from a global and international perspective. And Michaela, I'd like you to talk about international collaboration in astronomy as well.
All right. So I'm going to go back to indigenous people showing us the way in which we can behave harmoniously, a way that's inclusive. And even when you have tribes that don't necessarily get along with each other, when they have common kind of watering places and land, they find a way to exploit the resource that's sustainable. We're not doing that. I don't want to accuse Mr. Musk of anything. Clearly, he wants to get to Mars. He's really focused on that. Like the whole Starlink satellite stuff, Tesla, like all this stuff is for him to get to Mars. Like he really wants to do that. When he does such a thing and people go there, who's going to tell him any different? Who's going to make up laws, rules on Mars and that sort of thing? I mean, you got to have to get there. What are you going to do about it, kind of thing? Before long, okay, just work with me here. People are going to be on Mars. You're going to have people born on Mars who've never been to the Earth. Eventually, they're going to grow up and they're going to be like, you know what? Why are we letting people from Earth come up with laws for stuff on Mars? We should come up with our own constitution, our own. You see where this is going? That's what's going to happen.
It sounds very much like season 1 of The Expanse. Yeah.
Answering a very different part of that question, I think. I think so. Astronomy is right now a very international science, partially by necessity and partially because we're stronger together when we work together. There's this sort of image of the lone genius astronomer, the Einstein sitting in the room solving all the problems of the universe by himself, and that is not the case now, and it really has never been. Most collaborations that are trying to answer these questions are number in the hundreds of people and cover 70 plus countries. The JWST was just even building the telescope was a collaboration of many, many countries in Europe, Canada, and the US. We've got several more telescopes that are sort of scheduled to launch or being built on the ground in the next 10 years. And they're all international collaborations. A lot of that is because it requires sort of the financial support of a lot of countries. But a lot of that is that there are astronomers studying in every country in the world. Barriers certainly exist on who defines like what the right way to be an astronomer is. And that's something that we're grappling with now. But astronomy is very much an international science, which is awesome.
Great. Thank you. All right. Let's see. Matthew Miller asks, what is Dr. Jha's vision of a coordinated launch and life cycle and de-junkification of space, requiring a ballistic payload to clear the junk out by steering it further out?
Yeah. So actually in in the whole Wayfinder thing in Privateer, where you see all those dots and all that other stuff, when things are far out, just like you said, they don't come back. We have accepted that when things die, they're just going to become part of an orbital landfill equivalent. So clearly, I don't believe that that's the right answer. Again, I really want to, try to motivate satellites being reused and recycled as much as possible, and that way getting more to this kind of idea of a circular space economy.
Michaela, this one is probably more for you. How might the SKA, the Square Kilometer Array, contribute and work with the James Webb Space Telescope?
Cool. Also kind of not my area, but it's cool. So the Square Kilometer Array is going to be really great for observing even earlier into the universe than JWST can. It's looking at it's looking into the radio, which is longer wavelengths, redder wavelengths. And because of what happens to light as it passes through the universe. I don't know if you've heard the term redshift, but that's one that I've tried to avoid using because it's just jargon. But what it refers to is that as light travels through the universe, it gets stretched by the expansion of the universe itself. And that stretching makes it go from a blue to a red. And so if you're trying to look at the very, very early universe, that light has been traveling for so long, it's gotten stretched so long, it's in the radio or even longer wavelengths. So if you have the Square Kilometer Array that's looking at the very, very early universe, and you can sort of compare it with the very slightly less early universe that JWST is looking at, you can start to build together. The SKA will look at the gas that formed in the early universe, and JWST will be looking at the galaxies that formed out of that gas. So they are very complementary.
Should we explain what they mean by array? I'm not sure most people will know.
Sure. So I don't know the details. Don't quote me on any of this, but what we mean by array is not, one instrument or one telescope. It's, I'm going to say 50 to 100. I don't actually know, but the idea is that if you put them across a large area of space, it's not space, the ground, you've now, instead of having a telescope or a radio dish that has a diameter of 5 meters, you now have a telescope or radio dish that has a diameter covering the entire field or the entire Earth. However wide you spread apart your radio dishes, that's how big the effective area of your telescope becomes.
It's how big it affects the resolving accuracy of it. The light gathering power is still the sum of the areas of the individual dishes, but the resolving power is set by the baseline.
Yes, exactly. Right? Yeah.
Great. You all have probably seen a radio telescope array if you've seen the movie Contact. Jodie Foster in that is in front of a real radio telescope array, the VLA, the Very Large Array in Socorro, New Mexico. And so same principle, but the Square Kilometer Array is going to put them on different continents on the Earth. And there's ambitions to put them on Earth and the moon to increase that diameter and thus resolving power. All right, let's see. Next question. Finn Staber asks a great one. How can local game development studios and interactive media companies in Texas help to build useful simulation tools and education experiences to support the rapidly evolving space industry and the future of space tech education? And I'm going to extend this to astronomy education as well.
That was a very intricate and nuanced question. I think that the answer is really in storytelling. Like, one of the things that people ask me, they say, what's the hardest part of solving this problem of space debris and space junk? Is it technical? Is it political? And I tell people, no, it's the lack of empathy. That's the hardest thing to overcome. Problems don't get solved because of an absence of empathy. Empathy is defined as the ability to project oneself into the perspective of another. Most people, when they lack empathy, they tend to say, that's not my problem, because they can't project themselves into that perspective and they see themselves as being independent of that. Oh, that thing that's happening on the other side of the planet, that's not my problem because it doesn't affect me. That doesn't affect me. Space doesn't affect me. That sort of ignorance. I fundamentally believe, and Privateer's ethos fundamentally rallies around the belief that all things are interconnected. And if you actually believe yourself to be completely independent of something else on the other side of the planet, you're not looking far enough. You're not looking deep enough. You're not looking long enough. Okay. My mission with Privateer is to show humanity evidence of this interconnectedness, to create empathy, recruit empathy, and from that place, hopefully be able to then recruit compassion, which is then the desire to solve the problem. Specifically, to answer your question, storytelling needs to be a part of it. Humanizing it needs to be a part of it. Most space people are just arrogant. They're elitist. They're like, oh, you don't have PhDs. You're not an astronaut. You're not a billionaire. You don't matter. I'm here to say you do. I am evidence that you do matter, because I could have chosen to do other things tonight. I have a 5-year-old waiting for me. I found it important enough to find somebody to take care of my 5-year-old to speak to you, because space belongs to everybody. I think that the film, TV, media industry can help the storytelling, recruit the empathy to then hopefully get compassion to solve these problems.
Yeah, that's a great question. I would say for the astronomy sort of astrophysics side, it would be awesome. And I think it's in line with storytelling to have, the challenge is making the science accessible. And I think the biggest sort of obstacle that we come up with is this concept that people have where it's like, I can't do it. I'm not good at math. I'm just going to write off that whole field. And astronomy is a very public facing science, and everyone can do math. You might not like it as much as I like it, and that's cool, but you can absolutely do it. And so I think it would be great to be having sort of public outreach and educational tools that make the astronomy much more accessible. We've got the cool pictures, but let's talk about, what you can learn from them and what they show us. I also, like, as a slightly separate statement, astronomy, especially now and certainly in the future, is turning into a very big data science. We have huge data sets that take up terabytes and petabytes, and so anybody who's interested in, working with tech to sort of working with some of those data sets are very welcome, because it's sort of new to the astronomers on how to handle all of that data.
I love that. Let me ask everybody here a question. Show of hands in the room. How many people in this room create knowledge or into creating knowledge? All right. How many people in this room are into creating solutions to problems? Everybody who raised their hand is a scientist and an engineer by definition. Those terms, science and engineering, are barriers to people getting involved. All of you are scientists and engineers. All of you that raise your hands, that's the definition of science and engineering. We got to get past the jargon and this terminology that's actually not inclusive and preventing people from coming up with really cool ways to solve problems and create the knowledge that we need.
Great answers. I'm going to ask a follow-up to that, though, because I want to dive in a little bit. The Austin Forum on Technology, we cover lots of different technologies throughout the year, including gaming technologies, which was the origin of this question. And it's always struck me that, and I think Morba hinted at it earlier when he talked about, these are not just positions for, elite few people to do, but maybe that perception exists so strongly that people don't study the math and physics they need, and they don't pursue the career that maybe they have all the aptitude to do. Can we overcome that with inspiration, storytelling? I love that answer. What about tools like virtual reality? When I was studying astronomy, it was often pictures, ironically, pictures in a in a book, two-dimensional pictures in a book. And I wished I could just go in to a VR type environment and understand space junk in 3D or understand galaxy formulation in 3D. Do you think VR has the technology to tell these stories better and maybe inspire people to overcome their misperceptions about whether they can do it?
Yeah, I mean, look, UT Austin has a Texas Immersive Institute. It's all about VR, augmented reality, that sort of stuff. And it's, again, all these things that you're talking about allows people to project themselves into different perspectives. And to me, that is, again, the definition of empathy and how to recruit empathy. So for sure, I think that there is a role for that.
Yeah, definitely. It's a little bit harder as you go out into too far out into the universe, because sort of VR requires a 3D mapping usually. And most things in the universe are so far away that you're only looking at it from one angle. You don't have the other angles to get 3D information. That's not entirely true. We have 3D information about some things. So absolutely, I think that would be awesome. I have looked at some images in VR and I could not take them off. It was just such an incredible experience. Astronomy is also, we're interested in additional ways to sort of create ways to interact with the data. And one of my favorites is called sonification, where you can take the information that you have, the data that you see in an image, and just similar to the way that we add colors to images, you add sound. So each brightness gets a different note, and then you can sort of play the image. And I think that gives you another way to interact with the data. If you're, hard of seeing or not, it's just a new way to experience the universe.
Back to this thing about, the physics and the math and that sort of stuff. I just want to let people know just very briefly, the way I started off in all this other stuff, I was a security guard. As soon as I graduated from high school, I enlisted in the Air Force. I got sent to Montana. I was guarding nukes, dark place. I'd never been in a place with such a dark sky. I saw dots of light going across the sky. I was curious. There were human-made objects reflecting sunlight. I decided, hey, I'm going to study aerospace engineering. I didn't start undergrad till I was 23, never took calculus before then, struggled all through undergrad, was not an A student, stayed up late trying to do stuff, barely got into grad school. And as a consequence of just determination, wanting to pursue my curiosity, I've navigated 5 things to Mars. I've testified to Congress. I chair related issues in NATO. So the thing is, everybody has this capability to do really awesome stuff. Just this idea that you have to just be really good at the math and the physics, and we put so much pressure on ourselves, this very performative, and that's not necessarily what's required to be able to make a difference.
More, but there's multiple questions in here about getting rid of space junk, pushing it out, knocking it out, et cetera. So I'm going to ask you, I'm going to collapse a few of these questions and say, in addition to coordinating the launches and the orbital paths and whatnot, what are there any viable techniques for cleaning out?
When it comes to this idea of cleaning stuff out, I believe that what governments need to implement is something called extended producer responsibility, which means extend the responsibility of end of life to the people producing the products, okay? Make them responsible to a great extent for this sort of stuff. When they have satellites, maybe they can get a third-party organization to take care of the disposal, then, the space garbage cleaning people, the dump trucks, the garbage trucks in space can go and rendezvous with these things, maybe bring these things back, hopefully burn up in the atmosphere, that sort of stuff. There is no great story. I mean, if somebody said, how do we clean the oceans? It's not going to happen. Like, the ocean will never be as pristine as it was several hundred years ago. That's not going to happen. Accept that reality. We have plastics in the oceans forever. How do we clean up some of it? But how do we prevent putting more of that stuff in? That's the right question.
I have a question from Larry Ketchersid, and I'm going to paraphrase it a bit. It's a little long, but the gist of the question is, there are satellites launched now that help us learn more about the Earth and understand carbon emissions, understand methane emissions, understand deforestation, et cetera. Can you go into a little bit more about what some of these greater good purposes of satellites are, in addition to the communications enabled by Starlink, which we all know about, and the satellite images? Can you talk a little bit more about some of the applications people might not be aware of that satellites give us that we can't get here on Earth?
I mean, I've been in talks with different countries in Africa, for instance, and the way that they, farmers in Africa don't necessarily have tons and tons of acres of land. It's very small land spots. They're trying to get, money and loans to basically occupy a very small plot of land, and they need to be successful or else they don't feed their families. Satellites can basically take a group of these farmers, be able to penetrate the soil, understand what the nutrients are, be able to use models and predictive analytics to say, these are the crops that are going to, grow. These are the things that are going to be successful. Given climate change, this is what we predict your yield is going to be, that sort of stuff that can actually help feed people. So yeah, that seems pretty critical to me, the ability to feed your family.
Great question and answer. And a related question from Cesar Nava. Are we going to be able to achieve world unity and world peace through space exploration?
Absolutely. Absolutely. So the thing is, space is where humanity, again, needs to go. And no single country, no single entity has the resources to do this by itself or by themselves. So absolutely, humanity needs to come together. And I believe that space is a unifying element. But the thing that can get in the way of that is ignorance of the masses. And this is exactly why everybody needs to kind of be educated and informed of who's doing what to whom in space and that sort of stuff, so that there's transparency. In the presence of transparency, collaboration can happen.
Michaela, do you want to answer this one too from an astronomy perspective?
Sure. I would say has anybody ever seen the image pale blue dot? I mean, that's basically my answer. Is I think astronomy gives you the ability to completely change your perspective, to really understand how absolutely tiny we are. And while there are plenty of other planets that are being detected, they are all incredibly far away. And while we have a lot of people, well, a small number of very rich people perhaps devoted to trying to figure out how to set up a new life, a new colony, I use that word very intentionally, on other planets in this solar system, that is never going to be the long-term solution. I mean, I shouldn't say never. That right now is not the long-term solution to the future of humanity. So astronomy gives us the perspective of saying, we have Earth, and we're relatively small. I don't mean that in a bad way. I find that inspirational, that all of the problems that we have on Earth are just stuck on this little tiny pixel in one image taken from within our solar system. So
I love that answer. I used to joke when I was a graduate student in the department here that if I went to a party and somebody asked me what I was studying, I would figure out a way to phrase, do I want to have this conversation or not? And if they didn't want to have the conversation, I'd say, well, I'm studying how degenerate carbon oxygen white dwarf stars explode and whether it's a deflagration or a detonation and what are the mechanics. And it's, oh, okay, fine. And then, but if I was being honest and I really wanted to talk about it, even though it was at a party, I'd say it's because it answers the big questions, right? Astronomy is about how did it all come to be? How did we get here? And I think those kinds of questions, instead of focusing on our differences, those are the things that you just got to. We're a small part of this overall universe. It's the only little home we have right now in it. And in relative to everything else, we're all the same. and we're all in this tiny little place, and we better take care of it and each other. So I really like that answer. And it was a great question, Cesar. We have a couple of sci-fi questions. You ready for a sci-fi question? We got time for two more. What is keeping us from building a Dyson sphere?
I really don't like Dyson to begin with. Like the whole thing, really Dyson, because the guy has a British accent, he's like, oh, you know, vacuum cleaner. I'm not really a Dyson fan.
I was really hoping it was going to be a different question. Sci-fi.
I've got a fun one for you next.
I don't know. I mean, honestly, I think, certainly money, and honestly, it is a cool theory that there's still a couple of holes in how that would actually work. Don't ask me what the holes are. I don't know.
I would say vast amount of money. And do we even want that? Because you want to see beyond that sphere to see the stars. And there's one fun question for you that Andrew Allen asked. How do we tell a galaxy's age?
How do we tell a galaxy's age? That's very hard. What we end up doing actually is trying to find the ages of the stars that formed in the galaxy. And one of the reasons why that's hard is because stars form at very different times. It's not just that a galaxy forms stars and then stops. It's sort of continuously forming stars, or there might be multiple generations. But it turns out that it's a little bit easier to tell how old a large population of stars is than a sort of much larger set of stars and gas. And galaxies are always, well, they're not always, but they're constantly smashing into each other and reforming and absorbing other galaxies. Like the Milky Way will eventually, Andromeda will eventually eat the Milky Way. So it's really hard to say how old a galaxy is. It's a little bit easier to say how old the stars inside the galaxy are. And then the assumption is that the stars formed in the galaxy, so you can put a limit to how old the galaxy is.
Great. That is all the questions, unless I did not select the one that our judges have picked as the winning question of the night. So tonight, for dealing with all of the AV issues that we had to deal with, we've rewarded that team that solved those, with them being the judging committee for the best question of the night. So Allison, Mary, or John, what question did you select? Was it one that I asked? Tabulating the three votes. Fraud. Yeah, let me get you the mic because I don't see that one. And announce the name of the person and the winner of the badge.
Winner of the badge, Ren Wilcox. Okay, her question is, how would leaders in this field encourage the general populace to become more involved in the advocacy for space environmentalism? And what types of consequences would be anticipated if environmental actions aren't taken?
Yeah, so the responsibility for damage and harmful interference and all these things in outer space falls squarely on states party to treaties in the UN, specifically the UN Convention on Liability and Damage, and the Outer Space Treaty of 1972, Article 6 states that states party to this treaty have the responsibility of providing authorization and continuing supervision of all space activities of non-state actors. So what that really means is that governments get to tell companies that they can launch and do stuff in space. And if they're going to license people to do stuff in space, they should actually have laws and rules regarding environmentalism and sustainability and hold these companies accountable for their behaviors because they're the ones authorizing them to do stuff in space. So we need to put pressure on governments to pass those laws and then enforce them.
fund universal health care and education for everybody.
I agree too. All right, let's give the speakers another round of applause. Thank you guys for being here with us tonight. We really appreciate it.